why QML question. Why QML? The goal of quantum machine learning is to utilize these quantum prospects like entanglement to solve data processing and machine learning problems. Now let's go over some examples of quantum machine learning methods. First of all is the quantum kernel method, where we try to distinguish or group data points into some groups using a simple hyperplane. See the image on the top right. The left image, let's say it's the original data distribution. We're trying to distinguish the data distribution, the green data and the red data. As humans, we can easily distinguish the two data points because the green data points are close to one another and the red data points are also close to one another. But if we're trying to select a simple hyperplane, trying to distinguish the two data distributions, it's not easy. So what we do in a kernel method is that we map the data points in using a feature space. For instance, that feature space has the z component as the distance from the origin. And in the new feature space, we can then find a good hyperplane that separates the data points. So that's what's done in a kernel method. In a quantum kernel method, the goal is to find a quantum unitary operation that maps the quantum states into a Hilbert feature space, and find a hyperplane in that space. So when is quantum kernel method used? Classical kernel methods are effective on their own. So we want to use quantum kernel methods only when the kernels represented by the quantum unitary operations are efficient only from quantum computing. In some cases, it can be, in other words, you can say that you use it when the classification of synthetic data has complex geometric boundaries. A researcher group, including Huang, published a paper in Nature Communications in 2021, investigating that the kernel differences from when using a quantum kernel and when using a classical kernel. When the geometric difference is large, using a quantum kernel method is more efficient. And also, we need to check if this is actually realizable. Actually, we need to check if there is a quantum supremacy in this type of quantum machine algorithm. So Liu et al. From IBM published a paper in Nature Physics in 2021, solving a problem derived from the discrete logarithm problem. They showed that using quantum kernel methods, they can exponentially speed up the problem-solving process. The next two methods in quantum machine learning are quantum annealing and quantum approximated optimization algorithms. We'll call it QAOA for short for now on. The reason I say talk about both of them together is that it's because they come from the same source, the adiabatic theorem. The adiabatic theorem in quantum mechanics is that when you have a system of state vectors that are eigenstates of a Hamiltonian, let's say H1, if we apply small enough perturbations, we can adiabatically move to the eigenstate of a different Hamiltonian. So the goal of quantum annealing and QAOA is to approximate this adiabatic pathway to start from an initial state and then derive a state vector that's an eigenstate of a desired Hamiltonian. Quantum annealing does this by just like sampling. It's like it doesn't try to accurately follow the adiabatic path. It just tries to like go through the pathway. We carry out many runs, and then between those runs, there is a one or two instance that we luckily land on the adiabatic pathway. Then we select that iteration and then go on and on. Quantum annealing is used to solve QUBO problems and is widely applicated in the industry. For example, finance, portfolio optimization, risk analysis. And as we'll see in the later example, there is also use cases in traffic analysis too. DB systems provide quantum annealing methods. The picture you see on the right is a qubit configuration. So we want the qubits to be able to interact with one another. That is, we want a fully connected graph of qubits. But the left graph, a simple fully connected graph, is not realizable physically because it's too complicated in between. So what the researchers at D-Wave Systems does is they construct a different pattern, which is like topologically same with that fully connected graph, but you call it a chimera structure. So it's more easy to implement. And then one advantage of this chimera structure is that you can compile a lot of different quantum circuits into that. So let's say we have a system of three quantum circuits that we want three qubits to interact with one another. We'll then group the qubit 1 and qubit 5 together so that they act as a single qubit, and then we use 1, 5, and 2 and 6 qubit. That way we can simulate the operations on 3 qubits using 4 qubits. And then since we have 8 qubits, we have a larger possibility. So this is quantum annealing. QAOA is quite similar to quantum annealing, but instead of like just shouting out the different trials that may land on a adiabatic pathway, we instead approximate the adiabatic pathway by moving through incrementally small steps. So if you're native to math, you can see in the methodology that we define a parameterized Hamiltonian as using the mixture Hamiltonian and the problem Hamiltonian. The goal is to arrive at the eigenstate of the problem Hamiltonian, but we start at the mixture Hamiltonian eigenstate. So in each step, we apply a unitary gate corresponding to a time evolution on the mixture Hamiltonian for duration of gamma j, and then it's the same for the Hamiltonian for the problem Hamiltonian for duration of beta j. The goal is to optimize the time durations gamma and beta so that we can accurately approximate the adiabatic pathway in the illustration above. QAOA is also used for qubit problems, and the most wide-known example is solving the max-cut problem. One real-life example, interesting example, is from the Volkswagen Group. They used a D-Wave connected service to analyze the bus traffic routing service for a seminar session for 4 days in Lisbon in 2019. The system was open online for 4 days, and it was operating real-time, routing the bus traffic using a quantum annealing software. QAOA also has many applications like portfolio optimization, and low autocorrelation binary sequences is when you're trying to generate a perfectly random noise signal, and also the max cut problem too. So quantum annealing and QAOA is like one of the most widely used applications right now. Next is the QNNs, which are quantum neural networks. Especially in quantum neural networks, there is a field called variational quantum eigensolvers, or VQE for short. Variational quantum eigensolvers are a type of parameterized quantum circuits. It's more close to what we know of machine learning because we optimize across the parameters using gradient descent or a different gradient method. You see the figure on the right shows a process for a VQE. A state is encoded into a quantum state, and then it goes through a parameter circuit, which is called an ansatz. Then the state derived from the ansatz is computed using a Hamiltonian. Then the computed Hamiltonian value is then fed into a classical optimizer, and then we perform a classical gradient descent on the parameters for the ansatz. The goal is to find the ground state of the Hamiltonian using tweaking the parameters of the ansatz so that the ansatz generates the ground state for the Hamiltonian. This seems very similar to what we do in traditional machine learning. But then why is VQE used? We see when you try to model physical systems, there's a limitation to the bitwise system of classical computers. We cannot actually model real-life physical values to infinite accuracy. But if we use variational quantum eigensolvers, because the states themselves are physical states, we can use this to model quantum chemistry systems as in their physical nature. As such, the QEs are used widely in quantum chemistry to find ground states of materials, molecules, and such. Two examples are here. The left example is the finding the ground state molecule energy of an HEH plus molecule using a photonic quantum computer. The red line here shows the theoretical values of energy to the atomic separation of the He and H plus atoms, and the blue dots are the values derived from variational quantum eigensolvers. The left example shows another example of a ground state energy estimation of the water molecule. This time they use a trapped ion quantum computer. You see that the orange dots, which indicate experimental values, are very close and include the VQE values in blue in their range of error. There are other methods in quantum neural networks that are being researched too. For instance, if you're familiar with the artificial intelligence fields, you will know that there is a method called generative adversarial networks, GAN. There is a quantum approach to using GAN, which we call QGAN. Since GAN is a generative model, the goal of QGAN is also to generate a distribution of quantum states. So QGAN is used to generate a distribution of quantum states, which is in turn used for state preparation of quantum amplitude estimation. And also attention models, which are the core models of large language models, is also kind of being implemented into quantum neural networks. There are various different approaches. One of them is a QSAM, quantum self-attention mechanism. This is used to sequence modeling, just like traditional attention. However, quantum neural networks, especially quantum self-attention mechanisms, are a really recently developing field, and there's no like fixed norm for it. And then there's no like real benchmark for it too. So to wrap, it was quite short. To wrap up, let's go over a quick reality check of these various quantum machine learning methods. The first method that we looked upon was the quantum kernel method, and it has high expressibility because we can map the states into a high-dimensional Hilbert space. But keep in mind that this does not guarantee quantum supremacy because we can actually express have infinite expressibility with classical data too, because we can map them into a function space which has infinite dimensions. But there are other advantages with quantum kernel methods when you can find a quantum kernel that is absolutely efficient for the system. The hardware is good enough. We can use NIST devices to run quantum kernel methods, but the applications are quite niche. So you have to select a problem set that can have a good enough quantum kernel. And the current research, although they suggest that they have achieved quantum advantage with quantum kernel methods, the advantages disappear under fair benchmark. That is, when we consider data state preparation and sampling, because like quantum systems have probabilistic outcomes, we have to sample them to know the actual amplitudes. Keeping that in mind, the actual advantages, the actual speed up of quantum kernel methods actually are not that much, even negative. So that's the drawback of quantum kernel methods as of it right now. And for quantum annealing and quantum approximated optimization algorithm, they are quite on the right side of quantum machine learning. So although the problem should be a cubic problem, which is kind of quadratic problem, but if we can find a cubic form or an Ising model form of the problem that we're trying to solve, we can use existing models from D-Wave or other NISQ model devices to solve it via quantum annealing or QAOA. One thing is that the problems, as we mentioned right before, is that the problem set that we can solve using quantum annealing and QAOA is not very universal. So that's the only problem. But QAOA and quantum annealing is used the most widely in the industry right now. Next, VQEs are NIST compatible. So we can run them right now with quantum computers that we have in the field right now. And their applications are critical for chemistry, pharma, material science. So these are the money-making fields. However, there are caveats. A key caveat in VQE and QNN in general is the baryon plateau problem. The baryon plateau problem is that when you increase the depth of the gates in the parameterized quantum circuit or the ansatz, when you try to derive the gradient of the parameters, you arrive at a plateau. That is, the gradient disappear. Many researchers are trying to resolve this problem, but there is no golden key solutions to this right now. So that's a key caveat. And also, since we are using a classical computer to compute the gradients and then send it back to the system, there is a classical overhead, and the latency of communication between the quantum computer and the classical computer can also degrade the time performance. So aside these two caveats, the performance of VQEs are good enough, and they can be used for quantum chemistry. And quantum neural networks have specific use cases for quantum-specific problems. For instance, QGANs are used for quantum amplitude estimations, which are just like a part of quantum circuit algorithms. Although some researchers try to use QGAN for just image generation or signal generation, like GANs are, but in those fields, quantum computers are not that efficient compared to modern day GPUs right now. So this field is still explanatory, and there has to be much more speed ups to go to compare directly with modern GPUs. But if we find a good enough problem set to apply quantum neural networks, we can use them to solve key essential problems for quantum circuits. So we looked at various QML methods. QML is not a single concept. In QML, there is a variety of applications from kernel methods, annealing, QAOA, VQE, and QNNs. They all solve distinct problems, and they have advantages in distinct problems on their own. The best performing cases often carry heavy assumptions on data, such as they have to be quantum specific or have to be on a certain group of data, and they are specially designed to perform well on quantum settings. So this is no golden answer like the current state LLMs are. The obstacles include data loading, trainability, many shot readouts, and baryon plateaus, and many more. So the core question for learners who are wondering what QML is would be this. Would QMLs drastically improve machine learning processes? Would we see, as in sci-fi novels, QMLs quantum computers replacing machine learning so that maybe maybe quantum computers will run ChatGPT in like 1 nanosecond. Will that happen? Right now, I think that's a wrongly sentenced question. After all, in engineering, there is no answer to every problem. For every problem, there is a specific problem case, and you have to find a specific model or a engine to solve that problem. Current state LLMs being able to solve like a variety of problems is very specific. It's very odd. Most of the cases, it's not like that. Machine learning processes were actually engineered to solve specific problems from the start. So what I think is that quantum machine learning will process the same steps as that. As we've seen that various quantum machine learning applications solve specific problems, we need to ask specific questions that quantum machine learning can have advantages in. For example, the QGAN has advantages in preparing states for a quantum circuit. So the next step will be how to use that quantum circuit or how to make quantum circuits that require quantum machine learning processes that can actually help the industry right now. So, to summarize in short, QMLs might not replace classical AI right now, but it can act as a good, efficient solver for some specific problems. Thank you. 네, 혹시 질문이 있으실까요? 네, 없으면 여기까지 하고 다음 분께 넘기겠습니다. 감사합니다.
네, 수고하셨습니다.